minimize that. And hopefully the audio is going in, and if it isn't, it's not a big deal. All right, so explaining physical properties, intermolecular forces. This, again, is very much a review type of what you did in the past. Yes, we do want you to write this down. Let me just see if we can, no, we'll back up. So again, the whole unit is on properties of solids. So our understanding of the intermolecular forces, the attractive forces, is key to understanding what state it's in. Yep. Melting point and boiling point. Very strong attractive forces between particles. They tend to be solids, high melting points. Moderate attractive forces, liquids. And weak attractive forces, they're not attracted to each other hardly. And therefore those particles can move freely. They're gases. So what we want to look at today are those forces between the entities. Yeah, this device is struggling. Anyway, we'll keep going, see what it does. I think we're just going to end up with a video that has lots of noise on it again. Okay. That's okay. Yeah, I think it's malfunctioning. Don't think we got that sneeze. Okay. Types of attractive forces. And again, this is very much like last year. Intramolecular forces. That's not what we're worried about here today. Remember, intra means within. We've talked in great deal about the intramolecular forces up to this point. Ion-ion forces hold ionic compounds together. Covalent bonds hold molecular compounds together. So again, like I said, this is very much like last year. when a chemical reaction takes place, you've broken the intramolecular forces. You're breaking bonds. We are not interested in those in this unit. When we did our thermochemistry unit back at the beginning of the year, we were interested in the energy needed to break bonds. So again, examples of intra-ionic bonds, nonpolar, polar covalent bonds. Okay. And intermolecular forces. And that's the ones we are interested in for today and tomorrow and the next day. Attractive forces between neighboring molecules. Inter means between, and in grade 11 I would have said if you go down to Florida, you take the interstate, and it's the highway that goes between states. Or if you want your computer's network to talk to another computer network somewhere out there, you would use the internet because it goes between computer networks. So intermolecular forces are forces that exist between individual molecules. Depends on the type of molecule, and intermolecular forces are weaker than intra. When you heat something up, it melts first, then probably boils, and then when you get it hot enough, you might be able to initiate a chemical reaction, but you very rarely have a chemical reaction before it melts, because the intermolecular forces tend to be weaker than the intra, the things holding them together. That's not true for everything. There are chemicals that you heat them up a little bit and it'll decompose. You'll initiate a chemical reaction even before it melts. So there are situations where that's the other way around, but for the most case, you melt it, then you vaporize it, and if you heat it super hot, you might blow the atoms apart. You might get the molecule to fall to pieces. Okay, now this is just an example type thing. I'll bring the whole thing up. And here, actually, I'll draw this on the, actually, no, my smartboard's lined up. I should be able to do this here. So in the past, right, we saw that this is going to be a polar molecule, and then we have our dipole looks like that. There's another dipole on that one, looks like that. So this slightly positive N to the H is attracted to that slightly negative N to the Cl. And you have a force of attraction because of this slight charge and that's our intermolecular force. Yeah, there'll be a slightly positive on that end and a slightly negative on that end as well. And that's exactly the way I drew it to you in grade 11 as well. Again, up to this point, it's really been kind of a review to what we did in grade 11. Now this is where it's going to take a little turn. Last year we just very quickly talked about the different types of intermolecular forces. We talked about ion-ion interaction. We talked about dipole-dipole interaction. We talked about hydrogen bonding, right? And then that was it. We very quickly defined it. What we want to do now is we want to quantify it a little bit. We want to make it something that's almost measurable that we can put some numbers with. Because that's what we want to do. And the next level is to learn about how we can analyze it more thoroughly. So this year, though, we're going to start with London forces, the weakest ones, and we're going to work our way up to the stronger ones. All right? Now notice we've got a new title there, Types of Intermolecular Forces Found in Small Molecular Compounds. We're going to learn in the next couple of days that there are some compounds that exist as absolutely huge molecules. We call them macromolecules. They're really big. Certain proteins you could think of as being huge macromolecules. But there's also lots of inorganic molecules that are really big. Diamond is a huge molecule, and we treat them differently. So what we're talking about here are what we call small molecular compounds, things like water molecules, or methane gas, CH4, or NH4. So we're talking about the little guys that we normally associate with chemistry. You haven't even been introduced to the large ones, but they exist. So that's why we want to differentiate between those. So these are just the good old regular small molecules that you've seen in various reactions over the years. London forces are due to the simultaneous attraction of the electrons in one molecule by the positive nuclei in the surrounding molecules. So all electrons that are in one molecule will have a very weak attraction for the proton in the neighboring molecule. It has to do with the fact that the electrons move around and expose these charges every once in a while. They exist between all molecules, anything with electrons. And in chemistry, everything has electrons. We're not talking about really high energy physics that might exist, say, in like the interior of a star, or maybe some kind of super furnace that creates very high energy plasma where the electrons are removed. We're talking just about regular molecules. The greater the number of electrons, the stronger the London forces and the higher the melting point and boiling point. And there's the new thing for grade 12. The more electrons a substance has, the greater the London forces and the higher the melting point and boiling point. Last year we would have said London forces are the weakest. They're just weak. But you can have really strong London forces. You just need really big molecules with lots of electrons. You have really, really big molecules, and they will be attracted to other molecules like it because of those electron to nucleus interactions. All right, so now at this point, we want to answer some questions. We want to do some comparisons. What's going to have the highest melting point, boiling point? And so we want to go through how we analyze these things. In other words, we're going to tell you how to answer the questions. That's what we do. Now, in the past, I used to bring handouts and hand them out to everybody, but since I'm out of the handout business, you're going to want to make a grid. I guess it doesn't have to have lines. Like, it doesn't have to have lines. And you know what? You don't probably need to write Lewis structure, because it's going to be obvious that that's the Lewis structure that we're drawing. Type of molecule, I'm looking for polarity here, whether it's polar or nonpolar. Total number of electrons. That's just adding up the electrons. So total electrons might be an important part of the grid. And I'm already giving you the answer to this. If we take a look at our periodic table, we can see that as you move from F to Cl to Br to I, we go from gases to liquid to solid. So let's see if we can make some sense out of it. These are all diatomic, so the Lewis structures are very similar. F, F. Don't forget your electrons. I'm going to give you questions like this on the test, and I'm going to ask for a Lewis diagram. I'm going to give you a grid very much like this. I'm going to set you up so that you can, go through the analysis. Please put your electrons on the Lewis diagrams. That's one where I just take a half mark off, like if you forget your electrons, especially on those outer atoms. So chlorine, chlorine, again, 6 electrons, bromine, bromine, and iodine, and iodine. Type of molecule. They're all, well, they're diatomic and their atoms are identical. So that means their delta En is equal to 0. And we will be doing delta En calculations. I'm just going to do it once for this guy, but all of them are equal to 0. So what kind of a molecule is this in terms of its polarity? It's nonpolar. The delta En is 0. So these are all nonpolar. 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 All right. So now total electrons. And total electrons means all of them. Even the inner electrons are important in this. This is a classic place where students make mistakes. Because when we draw Lewis diagrams, we only count the valence electrons. But when we count electrons for the purpose of looking at London forces, we need to count them all. So this is 9, not 7. So 9 times 2 is 18 electrons in that structure. 17 times 2, what is that, 36? 34? Can't do my math? 34? That's good. 34. Thanks for the help. Good. And 35 times 2, 70? I can do that one, maybe. And 53 times 2, 106. And you can see here the trend along with the trend of electrons. Gas, gas, liquid, solid. So we would say that I2 is greater than Br2 is greater than Cl2 is greater than F2 in terms of its melting point or boiling point. All right? And that's because it has stronger London forces. Stronger London forces. More electrons, the greater the London forces. The higher the melting point, the boiling point. Question? The London forces would be between two F2 molecules, and due to the only 18 electrons, it would be a weak attraction, hence it's a gas. But because there's so many electrons in the I2 molecules, that force is so strong that it holds them together as a solid. Why is mercury a liquid? You're asking that when we're talking about molecules? Let's save that for tomorrow or the next day. I think I do metallic bonding tomorrow. That's a metal. We'll talk about it another time. All right. The easy answer would be, it has weak intermolecular forces. But that wouldn't satisfy you, would it? Yeah, don't worry about writing the question. I always forget there's an animation there. You can just put there number 2. And you don't have to put rank in order of increasing boiling point. That's what we're going to do anyway. So if you've already started to draw your grid, that's excellent. No need to write the question itself. We're going to rank it. We want to know which one's going to boil the highest or melt the highest. It doesn't matter whether we talk about boiling point or melting point, right? Because they're both going to be higher or lower depending on those intermolecular forces. C2H6, CH4, and C3H8. So again, you don't have to necessarily wait for me. I'm just going to draw them up. So here we've got all single bonds in here. I'm not worried about the 3D Lewis at this point, right? Remember the delta En was about, I think it was about 0.3 something, which was greater than our 0.2, but less than our 0.5 that the new textbook has, right? So those, according to the new textbook, are all non-polar bonds. So we don't even have to worry about symmetry, non-polar, all right? Same with CH4. They're symmetrical as well, but it doesn't matter. Non-polar. And same with C3H8. Oops, that's right off the edge of the screen. And again, all of those bonds are less than 0.5 non-polar. So let's look at the electrons. Again, total electrons. The carbons are 6, right? So what do we got? 6 times 2, what's that? 12, 13, 14, 15, 16, 17, 18? 18 electrons? 18 electrons, what's that? 6, 10 electrons there. And 1, 2, 3, what did I say? 6, 18, 2, 4, 6, 8, 26? 26? Am I doing my math right? 26. Sorry? 26 is good? Okay. So, which would have the highest melting point, boiling point? C3H8. C3H8 is greater than C2H6 is greater than CH4. And again, that's for melting point, boiling point. And again, why it has the most electrons and therefore it has the greater London forces. You'll be asked to complete a logic argument that goes with that, and all you'd say is because it has greater London forces due to the increased number of electrons, right? So due to greater London forces, all right? Because it has more electrons. Okay? Now, this is only working because they're all nonpolar. If I have one that's polar, that changes the intermolecular force. We've got to then change our argument. But if they're all nonpolar, we're just looking at electrons. Okay? All right, moving ahead. Let's now talk about dipole-dipole interactions, and that's between two polar molecules. You do not need to draw this picture, but this represents a bunch of HCl's. You can see there the arrow pointing where the electrons go, and so you can see there's little dots that are linking the arrowhead to the positive tail, indicating there's some kind of force between those little dipoles, right? Remember, the little dipoles behave like little magnets. So when you have enough of these dipoles together, they're all going to hold together. It's a stronger intermolecular force. There's a little attraction between all those little dipoles that are existing there. The strength of the dipole forces depends on the polarity of the molecule. The more polar, the greater the overall dipole of the molecule, the stronger the dipole force. So we're going to be needing delta En calculations for this, because in order to compare them, we're going to need to know which one has the greater polarity. So if you need a table, you want to play along and do some calculating, that's great. If you have one, it's even better. So again, we're just going to be now, again, analyzing pairs and groups of molecules and seeing polarity and see which one is more polar and then making conclusions based on it. And again, various people are at different stages of writing, but I do need to proceed. Hold on one second. No need to write this down. In order to determine the effect of dipole forces on melting point and boiling point, we must compare isoelectronic molecules. In other words, we want to compare molecules that have the same number of electrons, because if we have varying numbers of electrons, the London forces could like almost dominate the dipole forces. If you have enough electrons, you actually can have stronger London forces than dipole forces. So we need to keep the electrons the same in order to make sense out of them. No, that you didn't need to copy it. I was just simply saying that in order to make a comparison, a valid comparison, we need to keep the number of electrons the same. Now, this is an iodine and a chlorine. All right, that looks a little goofy. It looks like an ICI, but that's an iodine and a chlorine because we want to maintain a diatomic structure. And we've seen Br2. So type of molecule, bromine, what is it? Nonpolar. ICl, we should do a delta En calculation. And what is, well, I'll take the calculation, I'll take the numbers, I don't care. Have you subtracted already? That's after the subtraction? 0.50, oh man, I never thought about our change in number there on that. That was not an effect before, but I'm going to say that that's polar. That's right on the edge of being polar. That's a good thing. I never even thought of checking that, whether that messed me up. So therefore, we're going to say it's a polar bond. Chlorine would have the higher, right? Chlorine's got the higher value. Yeah, with polarity starting at 0.5, yes. So that's fine. We're still able to say it's polar. 0.5 and up, yep, is polar, up to that 1.7. So total number of electrons, what did we do? Br is 70, right? And I and Cl is what, 17 plus 53, and that also makes 70, which is handy. So in this case, the London forces are the same. So it's not London forces affecting them. What are the intermolecular forces? Just London. In this case, it's London and dip-dip. Dipole-dipole interaction because of the polarity. So if we're going to rank them in increasing boiling points, I guess this was worded differently. Lower boiling point, higher boiling point. Br2 is less than ICl, since it said rank them in increasing boiling point. So I changed that sign over there. And why is that? ICl has stronger dipole-dipole interactions. What's going on here? My pen is doing all kinds of goofy stuff. I want to drag that up. Interactions. Oh, you silly thing. Interactions. All right. All right. Okay. Let's do another pair. Now, for these two, I have to do a calculation of the delta En. Now, Mrs. Garrett, who put this particular PowerPoint together, she liked to put the delta En down here, but I should maybe reorder it. I would put the delta En up with the type of molecule. So actually, I would do the delta En before I decide what type of molecule it is, because I want to see whether it's, if it's polar or not. Again, everything is exactly the same as we've been doing. We're going to draw a Lewis structure. Again, the tables seem to be very similar. I don't know how, how far ahead you guys are getting these. Sulfur, right, is in group 16, so it's like oxygen. So this looks a lot like water. I'm drawing it bent because it is, but if you drew it going all the way across, that's fine. I'm not asking for a 3D Lewis. But it is bent. Remember, it's sp3 hybridized, and so it's going to have two of those as being lone pairs. So it's a bent molecule. But it doesn't say 3D Lewis, so if you drew it straight across, I wouldn't care. So now we need some delta ENs, because I need to know whether the bonds are polar or not. And to be honest, I did all these examples using the 0.2. So we may even find that some of these bonds are just not polar at all, which would be different than my analysis in the past. But it doesn't matter. We'll follow the logic that we're given. Do we have delta ENs? What do you got? 0.38. 0.38, which for this one? 0.38, which is interesting because last time I did this, we used 0.2. We would have said that that's a polar molecule, but according to the new numbers that I said we're going to use, this now becomes non-polar. All right? Everybody kind of see that change? Now, let's keep going. What do we have for this one here? Do we got a number for that one? 0.96, 0.96, and therefore polar, and total number of electrons. All right, let's total it up. Sulfur is 16, 17, 18. 18 electrons, and chlorine is 17 plus 1 is 18. 18 electrons, so that's isoelectronic. That's good. So intermolecular forces, what's this? What are the forces this thing's feeling? Yep. Just London? London. And this guy here? London and dipole, dipole. So which one, we're going in increasing boiling point, so which one has the lowest? Which one will have the lowest boiling point? Boil at the lowest temperature. Yep. H2S. H2S. And we're going increasing, so it's less than, and that is HCl. This example is exactly the same as the example we just did, but last year when I did it, because I used 0.2, I would have told you to use this as the higher boiling point because of the greater delta En. Right? So if you've got two of them that are dipole-dipole, use the greater delta En. Now that's a simplistic representation because it's actually two dipoles being added together in this molecule with only one dipole in this molecule. But if you end up getting a question that has both of them London and dipole-dipole, simply use the delta En with the greater delta En being a stronger dipole and therefore a higher boiling point, melting point. Okay? That's why I did this question before, because they had a different delta En. They were both dipole-dipole, but with our new definition, this works out quite easily. We can see that the HCl would have a higher boiling point, melting point. Okay? All right? Yep. Yep. Okay. And let's do HBr and HCl and go through the logic on that one and see what we get. And Bradley's grown bored with my analysis of molecules. It's repetitious. It causes you pain, doesn't it? Repetition causes you pain? We just did HCl, right? I believe the delta En, it was 0.96, making that polar. Total number of electrons, 17, 18. Yeah, we just saw that too. You'd think I'd remember that. HBr, I don't know what the delta En is. 0.76? 0.76? Okay. And total number of electrons, 35, 36. 36 electrons. Type of molecule, it's polar as well. So, intermolecular forces. London and dipole-dipole for both, right? London, dip, dip. London, dip, dip. So, which one do you think has the greater melting point or boiling point? Yep. Why is that? Okay, that makes good logical sense. Anybody else have a different interpretation? Yep. Yeah. So I have no idea. I have no idea what the actual rank is. I could do a Google search and check it out, but I don't know what it is. But from what I've told you, there's greater London forces in HBr, right? But there's greater dipole-dipole interaction in HCl. So your answer to this, well, there's so many variations, it's inconclusive. We cannot conclude which will have the higher melting boiling point or boiling point because one has stronger London forces and the other one has stronger dipole-dipole forces. And there's no real way to just quantify it with the number of electrons. There's many different variables. So in this case, we're going to come up with inconclusive. Inconclusive, right? HBr has greater London forces, and HCl has greater dipole-dipole interaction. All right? So we can't tell. From what I've taught you, we have inconclusive at this point. Yep. I'd give you part marks, you bet. But then I would have said, hey, but what about the London forces? So, you know, if the whole table was, say, out of maybe a half mark each, 1, 2, 3, 4, 5, or something like that, and then I gave you, say, 3 marks for the argument, you'd likely use 1.5 for missing the other half of the argument, right? You see what I mean? So it wouldn't be a total, you know, catastrophe. It would be, oh, you should have also looked at the electrons as well. Yeah, and in this case, we can't say. We've got competing forces. We don't know exactly how great those London forces would be based on just looking at the electrons. Yep. If we knew more, what more information could we gain? Oh, interesting. Could you analyze this further in university? Well, probably, but I never actually had to do any of that stuff, whether you do that in a course. The delta En is not a direct measure of the strength of the dipole, all right? The strength of the dipole is kind of like saying how strong is this magnet, which really means how sticky is it to another magnet. So there are various equations that chemists have tried to come up with that relate the size of the delta En to the strength of the dipole. If you did that calculation, then you'd be getting closer to being able to actually calculate what force that dipole can undergo. Do equations exist for that? Yes, they do. Have I ever taken a course where I had to use those equations? No, I didn't. So maybe if you went down that particular focus or that path, you would use those equations. Yeah. Okay, moving on. All right, hydrogen bonding. It is lengthy. Now that picture off to the right is not a bad picture. It does kind of cover it. We're talking about molecules that contain nitrogen, oxygen, or fluorine that are then bonded directly to a hydrogen within that molecule. Notice in this image here that the one is an H and the rest of them are blank, because it doesn't matter what the other ones are. They could be all H's, they could be NH3, but they could be NH with a couple of Cl's, I guess. You'll notice here as well, for the oxygen, we've got the 2 lone pairs, the O and the H, and we leave that other bond blank because it could be something else, as long as an O is bonded to an H directly. This results in large delta ENs, meaning they're really polar, essentially. And because they're so polar, they're a very strong intermolecular force. They tend to dominate over dipole-dipole and London forces. And they're really important in biology, I think. I don't know. You mention H bonding once in a while. They all have London forces because they'll all have electrons. So when you're filling in that box on types, always put London first. Then look to see if there's a dipole, or if we've got nitrogen bonded to hydrogen, or oxygen bonded to hydrogen, or fluorine bonded to hydrogen, then you can say H bonding. All right? So yes, as you said, somebody told me at one point in time that it's here. Let me just jump ahead here for a moment. I get silk. I don't know. Again, I didn't make this. What is this? DNA? Something important there? DNA? Is that important? Is DNA important for something? No? Okay.
No,
So like we could get away without the DNA thing? Okay, I'm going to back up here. You can write that down before we do our examples. Excellent. Excellent. That's the first groan of the day. No, not even close. I've still got 23 minutes worth of solid writing. When I went back to look at the video, it was 1 hour and 8 minutes worth. If I take a look here, we're on slide, whoa, that says 15 of 30. Whoa, that's got to be a mistake. I don't think I at the very end, it goes into the solubility stuff, and I stuck that on the end of the other note that we did the other day, so I'm not using all of them. I already sent it up. How is a good golfer like a donut? They both have a hole in one. Not true, I've never got a hole in one. It's hard. Yes. Oh, that's exciting. So, for the sake of us being able to make arguments and answering questions, if you have something with H bonding, you're going to treat that like you've got, like, you know, the right Bauer in Euchre. It's going to trump everything, and it's going to have the highest melting point and boiling point. All right. Now, you like Euchre? Yeah, I don't. But anyway, that has nothing to do with anything. So, just for the sake of this, we're going to say if you get an H bonding molecule, it's going to be the one with the highest melting point, boiling point. That's not true. You can have big molecules that don't have H bonding, that are like London forces, like big plastic molecules, and they will have a very high melting point and boiling point. But we're not talking about those extremes. And so just for the sake of us being able to answer a question, I'm saying it's going to trump the others in this particular case. All right. So, again, various people at various stages. Yep, we get that. It's good. Oh, look at H2S doesn't even work anymore because H2S becomes nonpolar, right? Remember, because its delta En is lower than that 0.5. Oh, well. 'That should get you to the end of the class, I think. Get you there. I might need a few more after that, but I'm not sure. No? No problem. .3, what was it, the H2? 0.38, which sucks because that now makes it nonpolar, which means it doesn't matter whether it's got H bonding, it's going to dominate over it anyway, but that's okay. We'll go through the logic like we should. Delta En for O's and H, 1.24, 1.24. This is polar, very polar. Total number of electrons, 8, 9, 10. 10 electrons, 16, 17, 18. 18 electrons. London, we write it down for each one. And this is H bonding. and this is London, and last year it would have said dip as well, but nope, with the way we've got our numbers changed, it's non-polar, so it's just London. But that's okay, we still get the point across. This has got H bonding. H bonding is much greater than London forces, even though there's more electrons. We're saying it beats it. Yep. Yes. H bonding is the extreme of polarity. Yes. It has to be polar to have H bonds. Yes. All right? So, greater boiling point, melting point, H2O is greater than H2S. All right? H bonding is a very strong intermolecular, and I'm going to run out of room here. Why does that thing not move like it used to in the past? Intermolecular, and yes, it doesn't like it. Intermolecular force. Even though H2S has more electrons, even if H2S has more electrons, all right? You get the idea. The logic would be, oh, what about H2S? It's got more electrons. Its London forces would be greater. But what I'm telling you guys is hydrogen bonds for this particular course is going to dominate that. All right. Let me just take a look, see what we're doing here. I'm going to jump ahead. We'll do this one here. And this is going to be our last one because everybody's whiners, and I hate you whiners. So that's going to be the last one we do, and then we've got a couple of little notes on surface tension and stuff. Yes, yes, boo-hoo, boo-hoo, just write it down. Jeez. I guess you could go back and look at your other picture if you'd want. Yep. I just want to, these are all H bonding, and I just want to talk a little bit about how water is special compared to the other two. So if you just want to make a note up above, sure, no problem. Yes, I skipped one because of the whiners. Delta En was 1.24. 1.24. Because I want to compare it to the others that also can undergo H bonding. Right? I wanted to look at water for a moment. Because water is special. That's what the biology people keep telling me. So I have to treat it as special. Yeah, I do. That's why we're doing water again. Other delta ENs. Anybody do the math yet?
For NH3, it's 0.84. The other one?
Total number of electrons, 710. And 10. And 10. Nice. So we don't have to worry about London forces. And so these are all our three examples. They're all H bonding, right? Oh, sorry, London and H bonding. And London. London and H bonding. And London and H bonding. Okay, so what would we predict as being the order if we're doing increasing, or whether it's increasing or decreasing? Which one do you think would have the highest melting point, boiling point? HF. You would think HF. HF, you'd think, is greater than. Yeah, but I'm going to correct it in a moment. You're right, this is not the correct order. H2O, which is greater than NH3, right, due to larger delta En, right? Yep. 1.64 for NH3? Is that?
No, 3.04, yeah.
All right. Okay, because that's huge. Okay. Obviously, due to greater delta En. All right. But in actual fact, the actual ranking, and I'm going to put it here, is H2O is greater than HF, is greater than NH3. Hey, folks, let's finish this. Now, this particular link here used to link to a site that would show the three-dimensional kind of interaction between water molecules. I'm not going to link that to it. I'm not going to show it to you right now. But the shape, the bent shape of water, along with its delta En, results in 4 hydrogen bonds that can form between adjacent water molecules. NH3 with its 3 H's actually can form fewer than 4 H bonds because the H's are in the way, that three-dimensional shape of that tripod, as opposed to this flat bent shape does not allow for as many close interactions. Even with the HF, you don't have as many H's, and therefore you cannot make as many interactions. They're only kind of end-to-end interactions. So here with each of the 2 H's and its structure, its two-dimensional structure, water is able to form more hydrogen bonds than the other molecules, and therefore it is a higher boiling point, melting point, and hence water can exist as a liquid at room temperature, which is very important. Something about life, I don't know, something like that. One more. Full of words. You're going to be mad because it's huge. Other important properties. Hold on one second. Let's just go with this. Write that one down. We won't bother with the second last one. Other important properties that come from this interaction. And these are just various types of liquid properties that, that can exist for all substances, but is very prominent for water, and that is surface tension. If you've ever taken a, you're having a beverage, milk or juice or something, and you're filling that cup right to the top because there's a very little bit left, and you get yelled at because you leave, if you leave that little dribble at the bottom and put it back in the fridge, somebody's going to yell at you. So you pour that in. If you've ever tried to overfill a glass, have you ever seen that before, right? You overfill that glass? No? Ever seen that? I don't know, I'm just saying. The reason you can actually do that is surface tension, right? Those water molecules are attracting to each other on the surface of that water, holding on to each other due to the hydrogen bonding. So when you have high intermolecular forces, you have a very high surface tension. Water can do that. Capillary action. You would talk about capillary action again in biology. It's the situation of where you've got a very small tube, and the attraction of that liquid to the sides of the tube, along with attraction to itself, draws the liquid up the tube. That's supposed to say narrow. It's a typo. Up in a narrow tube. Viscosity, a measure of a liquid's resistance to flow. So a very viscous liquid does not allow flow easily. And vapor pressure, and that's its ability to evaporate. And if you were to compare, let's say you had a container that had either some acetone in it or even gasoline or even paint thinner to a container that has water in it, you can tell the difference, even though they can be clear colorless liquids. You can tell the difference just by having them in a container on a table or on a bench or whatever, because the gasoline, the surface of it really ripples very quickly, right? It moves very quickly because it doesn't have a lot of tension holding onto that surface, where the water waves are a little slower. If you jiggle it in the container, the non-polar substance settles itself down very quickly, where the polar substance like liquid sticks to the sides and slowly works its way down back into the container, right? So you can actually see the difference by looking at some of these properties. Okay, that's the end of this at this point. There is a worksheet that is online. There are no text questions, and it just asks you to analyze various pairs and groupings of molecules in a very similar fashion to what we did in this lesson. Again, essentially, what did we talk about? We talked about those intermolecular forces, London, dipole-dipole, hydrogen bonding, and right, London, you're essentially counting electrons. Dipole-dipole, you're looking for the delta En, and then hydrogen bonding, you're looking for those specific examples where hydrogen is bonded to nitrogen, oxygen, or fluorine. Okay, that's that.